Welcome to Deep Dive Lab, where we break down and dissect cutting-edge scientific research, from advanced biomedical technologies to breakthroughs in AI, material science, chemistry, and physics, all told as compelling, easy-to-follow stories.
And today we're heading straight into some of the most extreme environments imaginable.
Yeah, literally the most extreme. I want you to picture a classic Hollywood sci-fi scene. You know the exact one I'm talking about?
Oh, definitely.
A spacecraft is violently shaking,
Yeah.
right? The view out the window is just glowing red hot as it re-enters an atmosphere.
Right.
Think of that absolute nail-biting re-entry sequence in Apollo 13, or really any Star Wars ship that's plummeting toward a planet's surface.
Yeah, that glowing red fire you're picturing in those scenes, well, that's plasma.
Just raw plasma.
Exactly.
Yeah.
It's generated by the sheer unimaginable friction of a physical object hitting a planetary atmosphere at, tens of thousands of miles per hour.
Which is just insane to think about.
It is. The aerodynamic heating is staggering. It basically creates this shock wave of superheated gas that envelops the entire vehicle.
Right, and you've seen it in the movies.
Yeah.
But if you were actually sitting inside that capsule, the only thing keeping you from being instantly vaporized is just a few inches of a heat shield beneath your seat.
That's it, just a few inches.
And that leads us into the core puzzle of today's deep dive. Here's a strange question. Why is it seemingly impossible to build a spacecraft shield that is both as light as a feather, but as indestructible as dragon scales?
Yeah, it's a great question. Because for decades, the laws of physics have essentially dictated that you can have one or the other, but never both.
Right.
Engineers actually call this the density versus ablation trade-off. Historically, when you're designing thermal protection systems, you were forced to choose between two, fundamentally flawed options.
Okay, let's unpack this. What's option one?
So option one relies on polymeric ablators like PICA, which that stands for phenolic impregnated carbon ablator.
CEA, got it.
Yeah, and these are heavily used on Mars rover missions, for example. Because they are highly porous and mostly empty space, they are fantastic thermal insulators.
Because the heat struggles to travel through those void spaces, right, to reach the delicate instruments inside.
Exactly, but there's a huge catch.
Wait, if they're mostly empty space and carbon-based, wouldn't anything over, 2,000 Kelvin just cause rapid recession? I mean, they'd just burn away.
You nailed it. They literally sacrifice themselves during atmospheric entry. They burn off layer by layer.
Which seems terrifying. Why rely on a material that destroys itself? Why not just coat the ship in, I don't know, the same ultra-dense ceramics we use for industrial furnaces?
And that brings us to option two, ultra-high temperature ceramics, or UHTCs.
Okay.
These are materials based on transition metals like zirconium or hafnium.
Right, the heavy stuff.
Extremely heavy. Now, they can easily survive extreme heat without flinching, no rapid recession at all, but their mass density is incredibly high. If you were to coat a spacecraft in solid hafnium diboride, the mass penalty is catastrophic.
Oh, because every extra kilogram of heat shielding costs thousands of dollars in rocket fuel, right?
Thousands of dollars, and it directly subtracts from the scientific payload you can actually carry. You'd be flying a really safe rock with no instruments.
It sounds like choosing between a thick winter coat made of tissue paper that burns off you, or a suit of armor that survives the fire. But wait, ceramics are bad insulators too, right?
They are notoriously bad at insulating. Dense crystalline ceramics conduct thermal energy very efficiently.
So the armor survives the fire, but it just conducts the heat and cooks you alive inside anyway?
Exactly. You'd be perfectly protected from the plasma, but the inside of the ship would be an oven.
Okay, so engineers naturally must have tried to merge the two concepts, right? Like, take the lightweight insulating polymer resin and just load it up with the ultra-dense ceramic powders.
Oh, they definitely tried. Mechanical blending was the standard approach for years, but macroscopic physics kind of ruins the application. Well, when you try to mix heavy ceramic nanoparticles into a liquid polymer matrix, van der Waals forces cause the particles to agglomerate. They clump together.
Ah, like when you're baking and the flour just clumps up in the bowl.
Exactly. It is akin to trying to mix gravel into water. You never get a perfectly homogeneous suspension. You just end up with a composite that has these heavy, dense ceramic pockets and then weak, unprotected polymer voids.
And if plasma hits one of those unprotected polymer voids,
It burns right through.
yikes. But wait, haven't they found ways to fix those microscopic voids?
They have, but it requires these notoriously complex manufacturing cycles. Engineers have to use processes like polymer infiltration and pyrolysis.
That sounds expensive.
It is. You
Yeah.
basically soak a carbon fiber preform in liquid resin, bake it at extreme temperatures so it shrinks and turns to ceramic.
Right.
And that shrinking creates new microscopic cracks. So then you have to re-soak it to fill the cracks, bake it again, re-soak it again.
Oh, wow. Over and over.
Over and over. It takes months just to make one usable heat shield panel. And even then, the performance is still limited by those macroscopic weak spots.
Okay, so this is where the story gets really interesting. How did scientists finally figure this out?
Well, they completely bypassed macroscopic mixing. In a 2026 paper published in the journal Advanced Materials, lead author Yiming Yang and his colleagues
From where?
from the Institute of Chemistry at the Chinese Academy of Sciences in Beijing, they took the solution down to the atomic level.
The atomic level, not just mixing powders anymore.
Right. They engineered what they call a multi-metal-phenolic network, or MPN.
MPN. Okay, so instead of mechanically blending the powders, they basically created a molecular level solution within the polymer backbone itself.
Exactly. They isolated the individual transition metals that make up those ultra-high temperature ceramics, specifically titanium, zirconium, and hafnium.
Okay, the heavy hitters.
Yeah, and instead of mixing them as a powder, they chemically bonded the individual atoms directly to a quasi-linear polymer chain. They strung the metal atoms along the polymer and then cross-linked these metal-loaded chains with a phenolic resin to create a nanoporous aerogel.
So instead of baking a chocolate chip cookie where the ceramic chips can clump up in one corner, they essentially dissolve the ingredients so every single crumb of the cookie has the exact same amount of metal and plastic.
That is a perfect analogy. Yes. Every nanometer of this material is completely uniform. The metals are woven directly into the molecular DNA of the plastic.
That is wild.
It creates a perfect balance without any agglomeration. But, a perfectly uniform aerogel sitting on a desk at room temperature doesn't solve the re-entry problem.
Right, because it still has to survive the fire.
Exactly. The true test of this MPN material is what happens when it's blasted with a 2900 Kelvin oxyacetylene blowtorch.
Wait, 2900 Kelvin. That is hotter than molten lava.
Much hotter. Under those conditions, a standard polymer aerogel instantly vaporizes. Just poof, gone.
Obviously.
What's fascinating here is what the MPN composite does. It undergoes a real-time transformation called in situ ceramization.
In situ ceramization. So it turns into ceramic on the spot.
Yes. It actively uses the extreme heat to build its own armor.
Wait, really?
Yeah. When that 2900 Kelvin plasma hits the surface, the hafnium and zirconium atoms instantly oxidize and forge into a rigid, microscopic, crystalline skeleton.
Hold on, let me push back on that for a second.
Sure.
If the surface is immediately transforming into a rigid ceramic crystal, wouldn't the sheer aerodynamic vibration, the immense pressure of atmospheric reentry, wouldn't that just shatter it?
You would think so.
Right, because a rigid crystal is inherently brittle. I'd expect it to crack from the shaking and let the plasma straight through to the underlying carbon structure.
And that is the exact physical vulnerability the researchers solved by including that third metal, titanium.
Ah, the titanium. I was wondering what that was doing there.
Yeah, while the hafnium and zirconium are forming that brittle, high melting point skeleton, the titanium, along with silicon, derived from the phenolic resin, oxidizes and melts into a viscous, glassy liquid. A super hot, flowing, glassy liquid. And because the metals were dispersed atomically, this liquid is generated uniformly everywhere, and it flows directly into the microcracks of the hafnium-zirconium skeleton.
Oh, wow. It's like building a brick wall where the mortar is constantly flowing and self-healing.
Exactly. They call it a co-continuous interpenetrating barrier. The hafnium and zirconium act as the rigid, load-bearing bricks, and the titanium-silicon melt acts as a dynamic, self-healing mortar.
So if the aerodynamic stress causes a tiny microfracture in the skeleton, the glassy mortar just instantly flows into the gap.
It absorbs the stress and kinetically seals the void, right on the spot. It completely blocks any ambient oxygen from penetrating deeper and destroying the interior.
That is brilliant. It literally uses the heat that's trying to destroy it to forge a virtually impenetrable surface seal.
It really is. But surviving the ablation at the surface is only half the battle.
Right. We still have the deep freeze problem, the insulation. We don't want the astronauts or the computers baking inside.
Exactly. The extreme thermal energy is still trying to push its way through the hull. But beneath that newly formed ceramic armor, the intense heat causes the interior of the MPN aerogel to evolve into a mass fractal carbon ceramic network.
Okay, mass fractal carbon ceramic network.
Wow.
What does that actually look like? Let's dive into the physics of how heat actually transfers through a solid.
Good idea. So, heat moves through solid, non-metallic materials primarily as phonons.
Phonons.
Right. They're essentially quantized vibrational waves traveling through the atomic lattice. If a material has a highly uniform, continuous crystalline structure, like those old heavy ceramics, those phonons travel relatively cleanly.
So they just conduct the heat right through from one side to the other.
Exactly, but a mass fractal geometry completely disrupts that propagation.
Because it's not a straight path anymore.
Far from it. A mass fractal structure is essentially this infinitely complex, self-similar, three-dimensional maze at the nanoscale.
A nanoscale maze.
Yeah, and the characteristic length scale of the newly formed ceramic nanoclusters within this fractal maze is actually smaller than the phonon mean free path.
Oh, meaning the heat wave is physically larger than the hallways of the maze.
Precisely. So when those high-energy phonons try to propagate through this interior, they don't have a straight path. They constantly hit the intricate, jagged boundaries between the carbon matrix and the ceramic nanoclusters.
So the material itself operates as a geometric trap for the vibrational energy.
Exactly. The phonons scatter wildly off these nanoscale interfaces. They just bounce back and forth, losing energy through boundary scattering and what we call phonon collisions.
The thermal energy simply cannot establish a direct vector through the material. It hits thermal dead ends.
It's beautiful physics, and the empirical results from the paper validate this mechanism perfectly.
Let's hear the numbers, because this is where my mind was completely blown.
So the researchers exposed this composite panel to the 2900 Kelvin torch for 600 seconds.
10 full minutes of continuous extreme plasma heat.
10 minutes. And the material demonstrated near zero recession. It lost just 0.0031 millimeters per second.
That recession rate is practically unheard of for a lightweight polymer-based aerogel. It basically didn't burn away at all.
Not at all. And for the insulation test, they exposed the material to 2500 Kelvin for 25 minutes.
Almost half an hour of continuous thermal assault.
Yep. And after all that, the backside of the shield experienced a thermal gradient of only 369 Kelvin.
Wait, 369 Kelvin? That's less than 100 degrees Celsius.
Barely boiling water temps on the inside, while the front face is dealing with blazing sun-level plasma.
That is mind-blowing. The interior stays well within the operational temperature limits for basically any sensitive electronics.
They completely shattered the density versus ablation trade-off.
Yeah, they really did.
By controlling the architecture at the atomic level, they achieved the ultra-light weight of a porous polymer, the thermal insulation of an aerogel, and the indestructible ablation resistance of a heavy ceramic all-in-one unified composite.
So what does this all mean? Let's zoom out. If you can maintain that level of thermal protection without the mass penalty of a solid ceramic shield, that fundamentally rewrites the weight budget for deep space missions, right?
Oh, absolutely. Think about the missions we are currently planning. We want to send robotic probes plunging into the crushing, scorching atmosphere of Venus.
Which is notoriously hostile.
Unbelievably hostile. Or the extreme environments of gas giants like Jupiter. The constraints on those missions are defined entirely by mass.
Because every ounce counts when you're launching it on a rocket.
Exactly.
Yeah.
And returning a sample vehicle from Mars, for example, means hitting Earth's atmosphere at blistering reentry speeds. Every single gram of heavy heat shielding you are forced to add just to survive that friction is another gram of scientific equipment you have to leave behind on Earth.
You literally have to choose between safety and science.
Right. But this MPN material proves we no longer have to compromise. You can design a ship that is incredibly lightweight, but still capable of surviving a brutal, long-duration atmospheric entry.
And there's an engineering aspect to this paper that we really need to highlight, specifically regarding manufacturing. Because miracles in a lab are great, but if you can't mass produce it...
It's useless.
Right. Earlier, we discussed how manufacturing those old UHTC composites traditionally required those agonizingly slow, month-long processes, mostly because heavy ceramics do not flow into molds.
Yeah, that was the big bottleneck. But because Yang's team started with a liquid polymer resin where the transition metals are atomically bound directly to the chains, the precursor maintains a very low viscosity.
It pours like a liquid.
It pours easily. And this allowed the researchers to utilize a highly standard, very common industrial technique called resin transfer molding, or RTM.
Which changes the game completely.
Completely. They just injected the liquid precursor directly into a mold containing a dry carbon fiber preform under standard pressure.
And how fast was this compared to the old month-long process?
They manufactured a fully integrated large bulk panel of this composite in under 48 hours.
48 hours. That is a massive leap from theoretical chemistry to practical aerospace engineering.
It really is. This isn't just some microscopic flake of a miracle material in a billion-dollar laboratory. It is a scalable, cost-effective manufacturing process that is actually ready for industry right now.
Imagine what this means for the future of commercial spaceflight. I mean, the exact same molecular technology keeping a multi-billion-dollar NASA probe safe as it dives into Venus that could serve as the lightweight shielding bolted onto a commercial orbital shuttle.
Exactly, the one taking you to orbit.
Right. It decreases the overall mass of the ship, which dramatically lowers the fuel costs of reaching orbit, while significantly increasing the safety margin for the passengers during re-entry. It makes space travel cheaper, lighter, and vastly safer.
That's the ultimate goal.
So, distilling the core innovations from this research, we're really looking at 3 distinct scientific victories.
Yeah, let's recap them. First, by abandoning that old macroscopic mixing and moving to molecular-level programming, scientists completely solved the agglomeration problem that plagued aerospace composites for decades.
No more clumping.
No more clumping. Second, the material relies on that elegant in situ ceramization mechanism. It actively uses the extreme heat of its environment to forge a self-healing, interpenetrating barrier, the rigid hafnium-zirconium skeletons supported by the flowing titanium silicon glassy melt.
And third, the interior evolution into that mass fractal geometry. It provides unprecedented thermal insulation by kinetically trapping the phonons at the nanoscale. It maintains a low backside temperature even after 25 minutes of 2500 Kelvin exposure.
It's just a brilliant piece of material science.
It really makes you think differently about the physics of heat. We traditionally view extreme heat as a destructive force, right? An environmental hazard that fundamentally degrades and weakens materials over time.
Usually, yes, it's the enemy.
But here, the heat is the necessary catalyst. The environment itself is what activates the armor. Without the fire, it just remains a lightweight plastic aerogel.
And that is a profound shift in engineering. If we can chemically program a spacecraft's hull to actively utilize the destructive forces of its environment to forge its own defense mechanisms, it really begs the question of what other structural materials could be engineered this way.
Oh, that's an interesting thought. Like what?
Well, could we design skyscrapers with molecularly programmed concrete? Concrete that actually uses the violent kinetic energy of an earthquake to instantly harden and reinforce its own foundation.
Wow. Using the kinetic energy of the disaster to trigger a structural defense.
Exactly. If destruction is merely a catalyst for a new, stronger state of matter, what might scientists uncover next?
That is an incredible thought to leave on. Thank you for joining us in the Deep Dive Lab. If you want to keep exploring the invisible forces, the molecular mysteries, and the brilliant materials shaping our future, be sure to follow and subscribe for more science stories. Until next time, stay curious.